Okay, class, we're about to start Unit 2 Review B. It says, show your work to receive full credit. Be sure to include units where appropriate. Walmart offers a 2-pack of 15-ounce bags of nacho cheese Doritos for $7.65. Costco's offer a 64-pack of 1.75-ounce bags of nacho cheese Doritos for $32.99. It says calculate a unit rate in terms of ounces per dollar for Walmart. Include all units. Okay, so Walmart, they got 2 packs of 15-ounce bags. So what we could do here, if we do 2 times 15, we're dealing with 30 ounces. That's the first thing. Dealing with 30 ounces. Now, it says it costs $7.65. They want us to calculate the units with ounces per dollar. Now, typically, when you calculate a unit rate, usually it's dollars per ounce, but they want you to actually do the reverse. So then we would take our 30 ounces and divide it by the $7.65. Now, we would put this in our calculator. Try to pull up right now. So we would have 30 divided by $7.65, and that would give us approximately 3.92 ounces. 3.92 ounces per dollar. Because remember, when we're doing a unit rate, it's always divided by 1. Does everyone follow that? Now, you can write it like this, or you can write it like this. 3.92 ounces. And then you could do your division bar here, and then put the word dollar. So that means the same thing. Both of those mean the same thing. Okay, next. We will go up here to B. It says calculate a unit rate in terms of ounces per dollar for Costco's. Now with Costco's, we have 64 pack of a 1.75 ounce bag. So we'll take 64 times 1.75 ounce, and we will multiply that out. So we'll have 64 times 1.75, and that will give us 112 ounces. So now, since they wanted ounces per dollar, they tell us here that it costs $32.99 for this package. So we'll take this 112 ounces and divide it by $32.99. Now we'll put this back in our calculator. So we have 112 divided by the $32.99, and that will give us approximately 3.39 ounces per dollar. Or you can write 3.39 ounce per dollar. Either way is fine. Okay, next. We come here to option C. Next, we come here to option C. It says, which option is the better buy? Explain your answer. Okay, now, whichever one gives you the larger amount of ounces for $1, that's the better amount. So it turns out that the 2-pack of 15-ounce bags give you more ounces for your dollar, because you're the consumer. The more ounces for your dollar you get, the better it is for you. Does everyone follow that? So then you would say the 2-pack 15-ounce bags from Walmart is the better buy. because you get more ounces per dollar. So you get more ounces per dollar, which makes that the better buy. Any questions? No questions. All right. Now, we go over here to the back. Oh, did I flip it too fast? Oh, okay. All right, so we go to the back here. It says Usain Bolt. Wait a minute. Okay. It says Usain Bolt holds the world record for the 100-meter run. He ran it in 9.58 seconds. Calculate a unit rate in terms of meters per second. So we want our answer to be in meters per second. So they said here that he ran 100 meters for 9.58 seconds. So we want our unit rate. Remember, unit rate is divided by 1. So we will have to take our calculator and take 100 divided by 9.58. And that would give us, it'll be approximately 10.44. We round to 2 decimal places. 10.44 meters for every 1 second, or we could write it as 10.44 meters per second. Either one is fine. All right, determine Usain's speed in terms of miles per hour. Now they tell us here, they give us values for miles to kilometers, meters to feet, and miles to feet. So they want us to convert this. They want the speed in miles per hour. So remember, we had 100 meters for 9.58 seconds. So now, we want to change the meters to miles, and we want to change the seconds to hours. So look at what we have here. We have 1 meter is equal to 3.28 feet. So we'll put 1 meter here, 3.28 feet here. Now we have feet to miles. It's 5,280 feet for 1 mile. So this would take care of our miles portion. Now we want to take care of the seconds. We want seconds to go to hours. Now we know, if you notice here, they do not write seconds to minutes and minutes to hours because you're supposed to already know that. 60 seconds in a minute, 60 minutes in an hour. So with that being said, we have 60 seconds for 1 minute, and then we will have 60 minutes for 1 hour. Now, as far as my placement of these values, remember, we're trying to get rid of those units. We want miles to only be in our numerator, and we want hours to be in our denominator. So here, since meters was in the numerator, we had to put meters in the denominator. Since feet was in the numerator, feet had to be in the denominator. That got rid of this here and just left us miles. Seconds started out in the denominator, so seconds had to be in the numerator. Minutes was in the denominator, so minutes had to be in the numerator. And that leaves us hours in our denominator. So when we multiply all of this, we will have here, just doing the numerator, we have 100 times 3.28 times 60 times 60. So that'll be 1,000,000 180,800 divided by, we will have 9.58 times 5,280. And so our denominator would be 50,582.4. Now we're going to divide these two values. $50,582.4. So when we divide these two values, we will end up having 23.34 miles per 1 hour, or 23.34 miles per hour. Now C, it says calculate a unit rate in terms of minutes per mile. Now, basically, we could take what we had in B here and stop here, meters per mile. But the problem is we want it flipped. We want the time on the top, distance on the bottom, right? So we can write all of this out, but instead of writing it like we see it here, we will write its reciprocal. So we'll start out with 9.58 seconds over 100 meters times, it'll be 1 meter over 3.28 feet times 5,280 feet all over 1 mile times, it'll be 1 minute over 60 seconds. Because remember, if we would have stopped here in the original problem here, we would have got miles per minute. But they wanted minute per mile, that's why we did the reciprocal. And if you see here, the meters would go, the feet will go, and then you'll be left with miles here. The seconds will go, and then you're left with minutes in your numerator. So now, let me put this in the calculator really quick. So we will have 9.58 times 5,280, which would be 50,582.4, and that would be minutes all over. We would take 100 times 3.28. I'm just doing the denominator here, times 60. So your denominator here would be 19,680, and that'll be miles. Now, when we do our final calculation here, we're just going to divide them. We have 50,582.4 divided by 19,680. So it'll be approximately 2.57 minutes per mile. Approximately 2.57 minutes per mile. All right. It says, what does your answer from C mean? For every 2.57 minutes, Usain Bolt runs 1 mile. Now, have any of you seen Usain Bolt run? Okay, let me tell you all this. If you ever see another clip of one of his races when he was going for the world record and everything, his time would have actually been faster than that. But a lot of times, I don't know why he started doing this. He would turn around and look behind him and smile at the people that was running behind him. And you know, when you turn around, that slows your time down. So his time would have been a lot faster had he just kept going and then smiled after he crossed the finish line. But I don't know why he did that. But hey. But anyway, let's go ahead to the next page. It says number 3. The following data is the number of wins and losses for the Detroit Pistons from 2008 to 2018. Complete the table by letting X equal the number of years since the 2008-2009 season. So let's do A. Since it's since 2008-2009, that means 2008-2009 would be the 0 year. 2009-2010 would be 1, and then so on. It's going in successive years, so you could just write these years down. So it'll just be 0 through 9. KB, draw a scatter plot using demos, well, it's supposed to be Desmos or Excel, of X and wins. Be sure to label the axis, paste the graph below, or submit the link in JetNet. Okay, so basically, you can have the years, and then they said wins. So on the side here would be the wins. So this would be the years, this would be the wins. Now, if you notice here, we go to 0 through 9, so we could go by ones. Then we know this would be our 0 year. Now, for wins, the most wins they have here is 44. The least amount of wins they have here looks like it's 25. So what I probably would do, I probably would go by maybe 3s. I guess I didn't anticipate that well. Oh, I was supposed to go to 44. I'm sorry. Actually, I should have did 4s. I don't know why I was thinking 39. It should have actually been 4s. So we would have 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48. All right. So we know down here on the side, that would be a 0 as well. So X, with X being 0, the wins are 39, which would be somewhere up in here. Then X being 1, the wins would be 27, which would be about right here. And then 2, we will have 30, which would be a little bit above 28. 3, we will have 25. Then 4, we will have 29. 5, we will have 29. 6, we will have 32. 7, 44. 8, 37. And finally 9, 39. All right. So that's an example of the scatter plot. Then it says, what does the scatter plot tell you about the Detroit Pistons? You say what? They're not very good. Okay, I'll put that down. They are not very good, but the wins were about the same for most seasons. Even though they were bad, they were consistently bad. They were consistently bad. You could set your watch by them. Cause what was it? It's 82 games in a regular season. Yeah, they only had 1 year where they made over half, which was the seventh year, 44. All right, next page. It says the U.S. Army is offering a one-time bonus of $16,000 for shipped to boot camp in 30 days, and a yearly wage of $25,558 for a specialist corporal, E4, with less than 2 years of experience. Write a linear equation modeling your total income assuming you ship in 30 days. So you have y is equal to, remember you get a bonus of $16,000. So we can write the 16,000 because you're going to get that within the 30 days, right? Then you can add on to your income because you would make $25,558 in a year. And we'll put an X with that, depending on how many years you have. So if we wrote this in slope-intercept form, we would just have to turn this around to 25,558x plus the 16,000. And this would be your formula. It says, how long would it take to earn $345,000? Now, here's the thing. This was a very bad question for me. And let me explain to you why this was a bad question. Because you only make this amount of money when you have less than 2 years of experience. To get the 345,000, you know that's going to take you more than 2 years. So technically, this formula won't be any good after 2 years. So I'm just throwing that out there, to let you all know. But in using this formula, we're still going to find this 345,000. So what we would do is substitute in $345,000. We'll substitute that in for y. We'll take our 25,558x plus the 16,000. We'll subtract 16,000 on both sides. So this would be 329,000 is equal to 25,558x. We divide these sides by the 25,558. And we'll round this to 2 decimal places. I'm going to put this in a calculator, but I'm not going to cover up everything. So it'll take about, we can round it to 2 decimal places. It'll take about 12.87 years. About 12.87 years. Now, number 5. It says the population of Tasmanian devils can be modeled by the equation y equals negative 12,610x plus 256,412 with a correlation coefficient of negative 0.966. where X represents years after 1996 and Y represents the number of Tasmanian devils. Identify the slope and interpret it in the context of the situation. Now we know this is in Y equals mx plus b form. So the slope is the negative 12,610. And it means every year since 1996, 12,610, I should say, well, 12,610 Tasmanian devils are, I don't want to sound morbid. I was going to say are no longer alive, but years since 1996, 12,600 Tasmanian devils are reduced from the population. Okay, B, it says identify the y-intercept and interpret it in context of the situation. The y-intercept is 256,412. So I write this ordered pair is the y-intercept, and it means the population of Tasmanian devils was 256,412 in 1996. That's all that means. Is the equation a good model for the population of Tasmanian devils? Explain. Yes, because the correlation coefficient is very close to -1. Because remember, we talked about correlation coefficient. If it's close to +1 or -1, that means that it's a good model. And a negative 0.966 is a good model. Any questions? All right. Just moseying right along. Now we go here to problem number 6. Now with problem number 6, it says, suppose you won Michigan's Mega Millions lottery ticket by matching 3 white balls plus the mega ball. Isn't it 5 white balls? Isn't it 5 and 1? Oh, okay. And invested your $200 payout, wait a minute, $200 payout in a savings account chosen by me. Your account balance is provided in the table. Oh, okay. So it's one of the lesser prizes. So you matched 3 balls and a mega ball, so you got $200. Okay. So it tells you that you got a $200 payout, and it was paid in an account picked by me. It says find the growth factor and growth rate. All right, now, I believe in the video I showed you all, to find out what the growth factor is, you take 0 and 1 years. Well, first of all, look at the years. Make sure they are consistent. So these are going up by 1 year, so they're consistent. And then what you're supposed to do is to go to the further year, just 1 year ahead, and then divide it by the previous year. So we could take 210 divided by 200, and then we could take 220.50 divided by 210. Now, of course, you could do the rest of them as well, but for the purpose of this and time, we're just going to do these two values and see what they come out to be. And I'm just going to divide these on the side, and these come out to be 1.05. So all the rest of them would come out to be 1.05. Now that would be the growth factor. And I'm going to abbreviate. The growth factor is equal to 1.05. Now that we have the growth factor, growth rate is easy to get because the growth rate, whatever your growth factor is, you subtract 1 from it, and then you make that decimal into a percent. So we could go off here, we could take 1.05 minus 1. That'll be 0.05. We'll move these two decimals to the right, and that'll be 5%. So we could use it. So the growth rate is 0.05 or 5%. So basically, you'll be making 5% interest. Now it says here, interpret the growth rate and factor in the context of the situation. Basically, every year you earn 5% interest. That's basically what it's telling you. You earn 5% interest every year. Okay, now C. It says write an equation to model the situation. Now, this is compound interest, and we know we're doing exponential regression. So the formula is y equals a times b to the x power. Now, let's take a look at these variables. A is always your starting value, or y-intercept, depending on how it's written. It's your starting value or your y-intercept. B is your growth factor. And then X is your time. So we really don't use this in years. Typically, we'll just leave the X the X. So we'll do Y is equal to. The y-intercept is when X is 0. So your y-intercept here would be 200. Now you can either get it from here or from the situation that was described here where it tells you that you got a $200 payout and that's what you were investing. So that was your starting amount. Your B, growth factor, we did that already, which is 1.05. Then we'll leave your XX. Now, just to clarify one thing, sometimes they would change your X value to become a T to represent time. You don't necessarily have to do that here, but if you see it, you would know why they switched the X to a T. Does everyone follow that? All right, now D. What will your account be worth in 70 years? Whew, okay. So we would have our X would be 70. Oh, you know what? Let me just rewrite this because this is how you're going to mostly see it. We'll make it T, which is time and T. So it'll become a T. So right here, this would just be T equals 70. So now we will have Y is equal to 200 times 1.05 to the 70th power. So we have 200 parentheses 1.05 to the 70th power. So this would be $6,085.29. Now we have E. It says, when will the account be worth $20,000? And they tell you to sketch the graph. Now, it says, when will the account be worth $20,000? We can substitute in 20,000 for Y. Is equal to 200 times 1.05 to the T power. No, okay, let's just go through this. We divide each side by 200. So then this will give us 100 is equal to 1.05 to the T power. Now, I know I did not go over this with you all, but I'm just going to show it to you by hand. Then I'll show you all how to do it in the Desmos calculator. We will have to use what is called a logarithm to solve this. So we will have log, the base would be 1.05 of 100 equals log base 1.05 of 1.05 to the T. Now on this side here, these two values will simplify out and leave you T. So now we need to go to our calculator. Now on our calculator, we will hit the keypad, and on the keypad, we will go to function. And when you go to function, you have to go to miscellaneous. And under miscellaneous, you will go to log A. Now under log A, it starts here with the base, which would be 1.05. Again, that base would be 1.05. Hold on 1 second. And then in the parentheses, it'll be 100. And as you see here, it gives you 94.39 years. So it'll be 94.39 years. I mean, yeah, 94.39 years. That's how long it would take for you to end up with $20,000. Now, there is a way we could do this in Desmos, which I had showed you all before. So let me clear up a few things here. It's not really that hard in Desmos, but I needed to show you all how to do this by hand so you all could see what it looks like. Okay, in Desmos, what we would do here is type in the equation that we had, that Y is equal to 200, and our parenthesis 1.05, and then we would take it, we'll take it to the X power, not to the T power. So again, that's Y equals 200, parenthesis 1.05, close the parenthesis, and then take it to the X power. Okay, now we will hit this wheel here and get us a table. So once we hit the wheel and hit the table, you notice here we have a table of values. So with the table of values, what we will have here with the table of values, we can either type in some values or we could stretch out the Desmos calculator and take this in until we find the values here. So let me just type in values here. I think this would be a lot easier. So if I type in 90 years, you know, we got $16,146, which is very, very close. As a matter of fact, let me see if I could do this magnifying glass. Let me zoom out. Okay, there we go. Now we can see the graph. All right, so I tried 95 years. You see we're a little bit higher than the $20,000. So then we could just play around with it. If we go to 94 years, you know, it's a little less. So we know it's in between 94 and 95 years. Now, as far as this graph is concerned, if we click on this graph, well, first we got to retype the equation. Once we get the table, we retype the equation. Y equals 200 times 1.05 to the x power. We could click right on the line, and then we could drag this. But first, let me pull this down a little bit, because we know we're in the 90s here on the x-axis. So I got to keep pulling it down. As a matter of fact, I'm going to have to change this a little bit from the x-axis. Make it 0 to about 100. Now if we click here, sorry for such short window space here, but to fit this all on here takes a little while. But here, as you can see, you can drag this, and you would just have to go up to the 90 something and you will see it. So it'd be 94.69. Let me go here. All right, here we go. Yeah, so it'd be 94 point, what did we come up with, 39? Yeah, so we would end up being at that range. So 94.39, and it'd be a little over $20,000. Okay, now that's basically it for this page. Now we move on to the next page. Well, let me go back here and show the answer. These were all the steps that we did. I got the 94.39. All right. Problem number 7. It says here, the following equation models the amount of caffeine in your blood system T hours after drinking coffee. Y is equal to 280 times 0.89 to the T power. Now that 0.89, that's really 0.89. Okay, so now it says, what is the decay factor? So when we do the decay factor, what we're supposed to do here is subtract, take 1 minus the 0.89. So our decay factor is 0.17. So that means that the decay of the coffee in your system goes down 17% every hour. And then it says here, what is the y-intercept? The y-intercept right here, remember we said that this a value, this is the y equals ab to the x. That a value is 280. So the y-intercept is 0 to 80, and that is the y-intercept. And they want us to interpret this. It means you start off with 280 milligrams of caffeine in your blood system. Now it says, how much caffeine remains after 6 hours? So we could take this equation and then substitute in 6 for T. Now when we put this in our calculator, what you can do at your leisure, when we put this in our calculator, it will give us a total of approximately 139.15 milligrams of caffeine that will remain in your system, that's in your system. Now it says, when will 5 milligrams of caffeine remain in your system? Okay, so basically they're asking us to do the same thing we just did in the previous problem. So we would take our formula, and we could put it right in our Desmos calculator. Let me try and pull that up right quick. So we could type in y is equal to 280, parentheses 0.89. Then we'll take it to the x power. And I'll type that equation in one more time as well. So I know I'm going to need this in order to slide on the graph. So with the second equation, I'll go to this wheel here and do the table. All right, now, one other thing. When you have another graph here, you need to turn that graph off or get rid of it. So you have exclusively the one line. All right, so now we have this graph here. We want to know when you would get 5 milligrams. So we could toy around with this. We could go 50 hours, that's too much. We can do 30 hours. That's looking a little better. 35 hours, too much. 34 hours. 34 hours is a little bit over that. So if we go here to 33.9 or 33, let me see. Yeah, 33 is too much. So if we do 34.2, 34.5, maybe 0.6, maybe 0.55. Yeah, it looks like it's 34.55 because 56 would be too high. So it'd be 34.55. So this would be approximately 34.55 hours. Now we could do that, or you could slide back and forth on a graph. So it's approximately 34.55 hours. All right, now, problem number 8. It says the following table shows the low-end FICO score and the typical annual percentage rate received when purchasing a car with a 36-month loan for $15,000. It says find an equation of best fit. Round parameters to 2 decimal places. Okay, so now we have our FICO score and we have our APR. So, okay, so this here, our FICO score would be X, our APR would be Y. All right, so now they asked us to find the equation of best fit. So what we need to do here is take our Desmos calculator. Let me go back up here. I want to wipe this clean. And we're going to type in these values. We'll put in a table, and we'll have 720. Then we will have 690, 660, 620, 590, 500. Now our Y value, even though we know this is percent, we just type the numbers as we see them. You would not change the decimal to reflect the percent. So we will leave the numbers as is. Okay. Now these are the numbers that we have here. So first thing we should try is the linear. So we have y sub 1, we will have to do the tilde, and then mx1 plus b. Now if you notice here, our correlation coefficient is negative 0.9522, which is pretty good. So now we're going to try the exponential regression. So it'll be AB to the x1 power. Then you have to click on log mode. And if you look here, your correlation coefficient is less. So the linear equation is the line of best fit. So we will write this, it says the two decimal places. It'll be y is equal to a negative 0.07x plus 53. And then we could put 0.00. This would be our equation. Part up. Okay, now it says state the correlation coefficient of the equation of best fit. That was the R is equal to a negative 0.9522. What does it tell you about this equation? The equation is almost perfectly linear. It's almost perfectly linear. Because if it would have been -1, it would be perfectly linear. And this is very close to -1. It says and just to show you all, if you forgot, on the calculator, it's this R equals here. That's the correlation coefficient. Okay, now, it says use your equation to predict the APR of an individual with a 300 FICO credit score. So X would be our credit score. So we would have Y is equal to negative 0.07 times 300 plus 53.00. Now if we put this in our calculator, this would be a negative 21 plus 53. And when we add these two together, that would give us what, 32? Yeah, so they would have a 32% APR. APR is 32%. That is sky high. That's because they have such a low FICO score. And I think that was the point. The minimum possible FICO credit score is 300. And banks typically require at least a 500 FICO credit score to be approved for a loan. Why might your prediction from C not be accurate? Well, if the banks stop at 500, at a 500 FICO score, there is no way to get to 32%. That's a quick and easy way of looking at it. If they stop at 500, you having a 300 score, you won't get there, according to that equation. All right. Now we go here to the back. Number 9. It says, according to TreasuryDirect.gov, the national U.S. historical debt outstanding is shown in the table. Complete the table by letting t equals years since 1954. Okay, so first of all, this would be 0, 1, and then from 9, that'll be 11. From 1954, that'll be 19. That'll be 24. What's that'll be 43. And here this would be 63. Okay, use a scatter plot in R to determine the best model of the data. Write the model around each parameter to 2 decimal places. So basically, they want us to predict whether or not that this would be a best fit and whether it's linear or exponential. So this is what we're going to do. We're going to go back. Now, this will help you out. You do not have to get rid of the table that you did. You could just replace the values in your table. And then since you already have the values in there for the linear and exponential equation, then it will automatically update. So let me just show it to you. 4, 43, 63. All right. We come up here. What's that? 271. 317. 458. 772. 54. Okay. We scroll down here. We look at our correlation coefficient for linear. It's 0.88. We look at our correlation coefficient for exponential. It's 0.979. So that would mean that we will use the exponential, and we have y is equal to a. It'll be 187.42. And then our growth factor will be 1.07. And then we would take that to the t power, as we state here. All right, so it says use the model to predict debt outstanding in 2018. Now remember, this is from 1954, so that's 64 years later. So we will have y is equal to 187.42 times 1.07 to the 64th power. So now we will put that in our calculator. 187.42, parentheses, 1.07, and then we would take this to the 64th power. So it would give us approximately 14,235.66. And we know that'll be in billions. So that'll actually be 14,235,000,000,000. So that's what it'd be in 2018. You know, that's very weird. Huh. That is actually... That was very weird. Okay. All right. It says, what is R and what does it tell you about the model? Okay. So R basically is the correlation coefficient. And so R is equal to 0.979. And that this model is almost perfectly exponential. The actual number of debt outstanding in 2018 was 21,516 billion. Calculate the relative error between your answer from B and the 21,516 billion debt outstanding. Now, one thing I would tell you is this here. If you notice, when we put this value in, and this is the problem with rounding. When we put this value in and had this multiplied and everything, we ended up with a less value than it was in 2017. But we know that the debt keeps increasing. Does everyone follow that? So that lets us know with all this rounding that we actually got a lower value than the actual. So remember, when we're doing the relative error is equal to the what's that? The estimate minus the actual divided by the actual. The estimate is what we have is 14,235.66 minus the actual, which was 21,516, and it's divided by the 21,516. So our relative error, we put this in the calculator, 14,235.66 minus the 21,516, that'd be a negative 7280.34 divided by 21,516. So it'd be a negative, if we round to, let's say 4 decimal places, negative 0.3384. And if we change this to a percentage, it'll be a negative 33.84% error. So the error, this will be off a negative 33.84%. Because remember, this is the estimate. All right, so we are done. And I hope this helps prepare you for the upcoming exam.